طيب بسم الله الرحمن الرحيم. So we started talking about medium access control, and we talked about the first medium access control mechanism, which is the simplest one, which is called ALUHA. So, and as we said, the best way to understand ALUHA is to imagine or to think about a roundabout with no prior attention from the drivers, if you will. And we have we have analyzed ALUHA, and we have noticed that the probability of collision is really high, and the vulnerable time is twice the transmission time, which is really large. And during that time, if there is any node trying to send, the collision will happen. And the main problem, the high possibility of collision happens because of the fact that there is no restriction for any of these nodes to send at any point in time. So for pure ALUHA, any node that has a frame is allowed to send immediately. There's no restriction on when the node will send. Okay? In other words, there's no restriction on the car to enter the roundabout. No restriction whatsoever. And that's the main reason for increasing the possibility of collision, because of that high degree of freedom. The second mechanism, or the slotted ALUHA, tries to resolve that slightly by restricting the nodes to send only in specific time slots. Okay? So by doing that, if a node has a frame, and this is the beginning of the time slot, then the node sends right away. If node like station 2, it has a frame here, then it has to wait for the beginning of the next time slot. It cannot send right away. That's the main difference. Okay? So for the pure ALUHA, if station 2 has a frame at this point, at this instance of time, it will send the collision and the collision will happen, right? So? But because we are using slotted ALUHA, the node will defer the transmission until the beginning of the next time slot, which will cause the collision not to happen. So just by using the simple notion of time slots, you can reduce the collision slightly. And we will analyze this the same way like we did for the pure ALUHA. So the only difference here is the specified time slot. So I'm only allowed to send in a specified time slot. So the advantage here is that naturally, I was able to reduce the collision probability. Okay? So, is there any cost that I have to pay in return? The time, yes, the instance of time. This instance of time has to be synchronized amongst all the stations. Yani all the stations, they have to follow the exact time slots, which in some cases is a problem, because remember that we're talking about multiple nodes, multiple stations with no coordination between them. They are distributed, maybe they are connected on a cable or something, but they do not have any kind of coordination. So, enforcing global synchronization through these time slots is tricky in that case, right? Because the nodes, they might have different clocks. They might have different clock speeds. Okay? Therefore, the synchronization between these nodes might be slightly problematic. Of course, there are solutions for this. So we can resolve this somehow. But I'm just trying to say here that there is a cost that we have to pay. And that's why the pure Aloha is the simplest, because I don't have to do any synchronization, I don't have to do any coordination, I don't have to do any sensing for the channel, whether someone else is trying to send or access the roundabout. I don't have to do any of this. I just send. Whenever I want to send, I just send, with no restrictions whatsoever. But we have realized that this complete freedom creates issues in terms of increasing the probability of collision. Just by specifying these slots, I was able to reduce collision, but I have to provide some synchronization. Okay. In that case, it turns out that the throughput for the slotted Aloha is the same, but without the 2 in the exponent. So G times E to the power minus G, not minus 2G. So the throughput here is more or less? More, right? Because the exponent, the negative exponent here is less, which means that the rate of decay for the throughput is less. So it happens that this throughut has similar behavior. So if we were to draw this throughput, it will be something like this. And at some point, G, which is the maximum G max, okay, it will start decay. The decay here is slightly slower compared to the pure Aloha. And it happens that G max here is 1. Remember that for the pure Aloha, the G max happens at G equal 1/2, right? Which means that the maximum throughput you can get when the system is half loaded, is loaded 50% of the time. Which means that the amount of frames or the amount of bits that are sent from all the stations collectively is 50% of the maximum data rate that the channel can provide. This is how we calculate the load. Okay? Here it happens that slotted Aloha has maximum throughput which is double. The maximum throughput here is double. If you remember, for the pure Aloha, the maximum throughput was 184.184, or in other words, 18.4%. This was the maximum, and it was at G equal 1/2. Here, the maximum is 36.8%, and it happens when the system is fully loaded. It happens if I'm trying to send collectively from all the stations the exact same amount of bits that the channel can carry per second. So let's analyze why we are getting this difference in behavior for the slotted Aloha. Why the slotted Aloha is better. The reason for this is that just imagine that we try to calculate the vulnerable time similar to what we did for the pure Aloha. If station A is sending, okay, then the beginning of the frame is at this time instance, and the end of the frame is at the end of the time instance, or the time instance of the next time slot. Right? So for each time slot, I'm allowed to send, and the frame occupies the whole time slot. Okay? So let's see. Similar to what we did for pure Aloha. So we'll see if we send a frame here at this instance of time, at this exact instance, the beginning, okay, then we will end slightly before the beginning of the frame of A. So, in that case, collision will not happen. So what happens if I try to send here? Well, can I? But can I? For the slotted Aloha, I cannot. So if just we assume that a station had a frame at this instance of time, what does this station have to do? It will wait until here. Okay? So the station will in fact send at this instance. And the collision will happen, of course, because A is sending at the same time. Okay? But the collision will not happen if I send here. If I send at this point, the collision will not happen. I cannot send here, I cannot send here, I cannot send here. So all this time is outside the vulnerable time. Okay?
So if it started late, the A and C will be shifted? Or
the what?
A and C.
Yes, so if for example, station C finds a frame at this point, it will not send. It will have to wait until this instance and then send. But the actual transmission time is here, not here. So in that case, only within this time slot, if any node tries to send, the collision will happen. Slightly before that, I cannot send. And if a node sends here, the collision will not happen, because at maximum, the frame will finish before this time slot. Right? And that's why the vulnerable time in that case is not twice the transmission time. It's exactly the transmission time. Because the collision will happen only if I send within this time slot. And for me to be able to send within this time slot, I have to have the frame available before that time. Okay? So in that case, the vulnerable time is equal to the transmission time. And that's why in the throughput there was it was G times E to the minus G, not minus 2G in that case. Okay? So similar to what we have done before, so the exact same example we have gone through last time, we will do it again for the case of slotted Aloha. So we have a slotted Aloha, in that case, a slotted Aloha system that transmits 200 bits for each frame. So each frame has a length of 200 bits, okay? And they share a channel of maximum data rate of 200 kilobits per second. So this is the exact same example. The only difference is that now it's slotted Aloha. So remember, for pure Aloha, we tried A, B, and C, 3 cases. For A, G was 1. For B, G was 1/2. And for C, G was 1/4. So where did we get this from? Simply that we know the fact that the transmission time is the length of the frame. The transmission time, So T transmission equal to frame length divided by the bandwidth or the maximum data rate. Okay, so the frame length is 200 and the maximum data rate is 200 kilobits per second. So the transmission time is 1 millisecond. Okay. So the transmission time is 1 millisecond. For the pure Aloha, the vulnerable time was, in that case, will be 2 milliseconds. But for slotted Aloha, it's only 1 millisecond. Okay. So what we need to do to calculate the throughput is simply to calculate the load. Okay. So if a system sends 1,000 frames per second, if the system, meaning collectively, all the nodes, they send collectively 1,000 frames per second. And we know that each frame is 200 bits. So this means that we have 200 kilobits per second collectively from all the stations. What is the maximum data rate of the channel? 200 kilobits per second. So the load is G is 1. So so for the case of G equal 1, what I need to do is that I know the throughput is G times E to the power minus G. So in that case, is G equal 1, which means that the throughput is simply E to the power minus 1. 1 over E, which is 0.368. 0.368 or 36.8%. This means what? This means that if you send 1,000 frames, you will get... I have to pick up this one. Hello? السلام ورحمة الله وبركاته. الحمد لله. أنا بس ما عندي كلاس دلوقتي حضرتك، بس في حاجة سريعة؟ طيب خلاص، حاضر أول ما خلص، مش مع السلامة. But this means that 36.8% of the frames will be sent successfully. So if I have 1,000 frames, this basically means that out of 1,000 frames, I have 368 frames will be accommodated, will go through successfully. The rest will, statistically speaking, the rest will be wasted through collision. Okay, so this means that only 368 frames will likely survive. And remember that for G equal 1, this is the maximum throughput. Unlike for pure Aloha, the maximum throughput was at G equal 1/2. But here, the maximum throughput happens when G is 1. So for the case of 500, the system is half loaded basically, because we have 500 frames per second. Each frame is 200 bits. So in total, we have 500 times 200 bits divided by the 200 kilobits per second. So that gives me G equal 1/2. So for G equal 1/2, the throughput is simply 1/2 times E to the power minus 1/2. And that happens to be 0.303, which is less than 0.364 or 0.368. So it's less. Because for G equal 1, this is the maximum you can get. Okay? So for S equal 0.303, and I have 500 frames, then I get out of the 500 frames, I can get 151 frames. So 151 frames will likely survive out of the 500 frames. Okay? The main thing is that here the throughput is less. If you remember for the pure Aloha, for this case it was the maximum. When G is 1/2, this was the maximum throughput. Which indicates that pure Aloha is probably good when the system is less loaded. Slotted Aloha allowed me to get the maximum throughput when the system is fully loaded. So the slotted Aloha is better than the pure Aloha, especially when G is more than 1/2. Okay? So if we were to draw the two techniques together, it will look like this. So if this is G, and this is S, so the pure Aloha will be something like this. And then at G equal 1/2, it will start decaying. Okay? However, for the slotted Aloha, the throughput will look like this. Will continue until G equal 1, okay? And then will start decaying. So that's the difference between the two. So just by allowing these slots, this allowed me to gain extra throughput when G is more than 1/2. Okay? And of course, for the 1/4, if G equal 1/4, then the throughput is 0.195, which is less than 0.301. Okay? So this means that I have only, if I have 250 frames times the throughput, so I will likely have only 49 frames out of the 250 frames will survive. Any questions? So the question is, the throughput seems that it's still, even with the slotted Aloha, it seems that the maximum efficiency or the maximum throughput that I can get is only 36%, which is really low. Okay? So the advantage is that both Aloha and slotted Aloha, they are still relatively simple. There's no restriction, I don't have to do anything special. But the question is, can I actually increase this throughput or increase the efficiency using any special mechanism? The first thing they thought about is that if I'm a car and I'm entering the roundabout, then what if I check if there is someone else in the roundabout? Which is what people usually do. Not all the time, but they usually do that. So if I do this, then for sure, I will avoid the collision. I will not eliminate it, of course, but I will probably reduce it a lot, and that's what I want. Okay. What does this represent in the communication systems? This actually means in the communication system that if I have a cable like this, and I have some stations connected to that cable. This essentially means that we are all sharing the roundabout. We are all sharing one cable here. So this means that before this node tries to send, it should listen to see, or it should check if there is any transmission happening on the line. Can I actually do that? Well, it turns out I can. Why? Because if a node is trying to send over the cable, the signal has some energy, right? The node tries to send some signal, and the signal has energy. I can measure the level of energy to see if there is some signal going over the line. So if I detect that there is some energy over the line, this means that most probably someone else is trying to send. So in that case, I will not enter the roundabout. So this is what we call in communication systems, this is what we call carrier sensing. Okay? So this is the concept of carrier sensing. So before any node tries to send over the shared medium, first it should listen to see if there is any energy over the line. If there is, then it should abstain from sending. So this way, I can in fact reduce the collision a lot. But why doesn't this eliminate the collision completely? Why? This example illustrates why. So if I have station B, station C, and station D and A are just listening, not involved in the transmission. So station B at time t1, it has a frame. It measures the energy level over the line. No one is sending, so we can see that, remember that this is the time, and this is the space. Okay? So this is time and this is space. So B has like some distance between B and C. Okay? And this is the time, which means that B, at time t1, it has a frame to send. Okay? Then it checks whether there is any energy over the line. It doesn't find any because no one is sending. At this point in time, no one is doing anything. So the channel is idle, so it sends. When it sends a signal over the cable in a form of broadcast. So anyone tries to send over the cable, it's a broadcast that it's actually a signal over the shared line. Okay? So anybody can listen to it. Okay? Here comes the space factor. So the space factor here is important. Why? Because at this point in time, B will send the first bit of the frame. Remember, what we are trying to send is a signal. And the signal propagates through the cable. Right? With a speed of 3 times 10 to the power 8, which is the speed of light. This is the maximum speed. Okay? So, B will send a frame, and the frame will be sent in a form of a signal which propagates through the cable. While it propagates, it takes time. That's why this line is diagonal. It's not horizontal. Why? Because the signal does not travel over the cable in no time. Right? It takes time. And here the times, of course, is in the form of, is in the scale of nanoseconds. Okay? But it takes time. So the frame will propagate in a form of a signal through the cable. Okay? So, for example, it reaches A at this instance of time, depending on how far A is from B, right? صح ولا متابعين ولا ماشي؟ And it reaches C here. So if C tries to listen at this point, it will not find anything. C, if it tries to listen at this point, okay, it will not find anything. If it tries to listen at this point, it will not find anything. Only when it tries to send at this point will it actually hear what B is trying to send. معايا? So this is very important. So C will not hear any signal from B until this point in time. Which means that the actual transmission happens at this point. So from here to here, so during this time, okay, the transmission is going on, but C cannot hear it. Right? The bad luck is that C at this point has a frame during this point. So it listens to the channel, and the outcome is A. Channel is idle or busy? Idle. So, even though the transmission is actually happening, but C cannot hear it because of the propagation delay. Okay? So in that case, C will transmit the frame and the collision will happen. So in that case, this area is the transmission of the frame of A, and there's no overlap between the transmission of A and the transmission of B and the transmission of C. Yani the two signals are not overlapping. Which means that at this point, A will hear that B is sending and will not detect the collision. Yani if A listens here at this point, yeah, let's take it from T1. For A listens at this point. Well, channel is idle. صح? A listens at this point. Oh, okay. B is sending. Okay? At this point, B is sending. No collision. Here, there is collision. Okay? Here, no collision. Because the transmission of B has already finished at this point. Okay? So that's a very interesting scenario that shows us the space and the time. And we should be able to know at any time here or at any location what's going on. Whether I can sense that the channel is idle, I can sense that only one station is transmitting, or I can sense that there is actual collision. As we will discuss later, is that each node, it measures the energy level. Okay? So at this point, let's say at T1, the energy level is almost zero. Here, at this point, the energy level will be the normal energy level, which is slightly high, but you can distinguish that energy level from zero for sure. So you will know that there is a station transmitting. There is one station transmitting for sure. How do you detect the collision? It's also easy. Why? Because if there are two frames sending, the energy level will be almost double the energy level that's happening in normal cases. So you have basically three energy levels. You have zero energy level, you have energy level which is P, which indicates that there is one transmission. If you have energy level which is close to 2P, this means that there is collision. 2P or 3P or 4P, this means that more than one station is sending at the same time, and there is collision. Any questions? Any confusion? Yeah, this gray area, during this gray area, there is collision. Okay, there is overlap between the two frames. Okay, so why do we need to highlight this? Is remember that this overlap depends on the time and the space, and it's very important. So if you want to know which station will detect the collision, you have to look at this area, okay, and to figure out what time and where exactly the collision will start, and after which time the collision will vanish. So for example, when is the earliest time you can detect the collision? That's a very tricky question. When is the earliest time you can detect the collision? C, that's true. صح, بس is there any other location earlier than this when I can detect the collision earlier? This point. Although there is no station, but if there is a station here, then this station will detect the collision the earliest. Because that's the beginning of the overlap in the earliest time possible. So if I were to have a station here, which in that scenario there is none, then this station will be the first one to detect the collision. And that's the problem with C, that C unfortunately detects the collision, or detects or hears B in a delayed time. So it sends blindly, and then later it will detect the collision here. Okay? So D, I can say that D detects the channel here is idle, detect one transmission, and then starting from this time, it detects the collision. And then if it senses here, it will still find the collision. If it senses at this point, then there's no collision, and so on. So that scenario is very important because it shows us both the space and the time, and when the overlap between the frames happen, in which case we know where and when to identify that a collision has happened. Okay? So the most important thing here is that carrier sensing does not eliminate collision. So that's why we have accidents and roundabouts. So just the fact that you sense before you enter, it doesn't mean that your estimation is really accurate. Okay? Okay, so similar to what we have done for the Aloha and slotted Aloha, what is the vulnerable time for the carrier sensing? Well, because we can do carrier sensing in that case, okay? Remember that if A tries to send, then the first bit will be transmitted in a form of an analog signal which will propagate through the line. And again, this line is diagonal, which indicates that the propagation delay takes time, right? So if B here, if it tries to sense at this time, it will find that the channel is idle and it will send, collision will happen, right? Also, if C tries to send at this point, then channel is idle, it will send, collision will happen, right? So if C tries to sense here, it will detect the transmission of A. In that case, it will not send. So collision will not happen, right? Which means that during the propagation time, until this transmission goes all the way through the cable, during that time, if anyone tries to send, the collision will happen, right? صح? Which means that the vulnerable time is the propagation time. So during this propagation time, if any node tries to send, the collision will happen. Okay? So for pure Aloha, the vulnerable time is double the transmission time. Remember, transmission time. For slotted Aloha, vulnerable time is 1 transmission time. For carrier sense multiple access, the vulnerable time is equal to the propagation time. Okay? Type. That's the vulnerable time. It turns out that of course the throughput for the carrier sensing is much, much higher compared to the Aloha and slotted Aloha. The efficiency can, in fact, get up to 90%. Okay? It's variable. And it depends on some other factors, some of which we will discuss. But the efficiency can get as high as 90% by doing the carrier sensing. Okay? Okay. Why do we say it's variable and it depends on some other factors? Let's look at the sensing. Okay? Let's look at the sensing behavior in details. So the sensing can be persistent in such a way that I say, is the channel is idle? No. Is the channel is idle? No. Is the channel, I'm going to be annoying. Is the channel is idle? So which means that I'm really persistent. Trying to detect the first instance when the channel is idle. So here, I'm continuously with very, very narrow time, I'm trying to sense, to detect the first instance of time when the channel is idle. Once the channel is idle, I will send. I will send right away. So this is what we call one persistent. One persistent means that you are very persistent in the way you sense, and once you find that the channel is idle, you send right away. Okay? So what's good and what's bad about this? Well, the good thing is that at least because I'm persistent, I will detect that the channel is idle once it's idle. Right? So that's good. That's what I'm trying to do anyway. I'm trying to detect the first instance when the channel is idle. So what's bad? The bad thing here is that this is in a way similar in a way with the pure Aloha, except for, of course, the carrier sensing part. But because of the persistence, Once the channel is idle, then I'll try to send. I will not wait for anything. Which causes a scenario like the one in the previous slide to happen a lot. That although someone else detected that the channel is idle and he tries to send, and you will not also wait for any time, and he will try to send, in that case the collision will happen. Because you don't give yourself a chance to really listen if someone else will try to send before you. So here, if I'm in a network with many stations, okay, and we all use the persistence strategy, the one persistence strategy, which means that we will be persistent trying to sense when the channel becomes idle. So the channel will become idle and both of us will send at the same time. Or with slightly different nanosecond time, which again, the probability of collision in that case is really high. صح? So the benefit here is that at least we try to avoid in some fashion to send during the fact that the channel is busy. So here we're talking about few nanoseconds, which is the vulnerable time that both of us will send at the same time and the collision will happen. So this is the one persistence. So on one hand, I'm persistent in detecting when the channel is idle, and once it's idle, I send right away. Okay. There is the other strategy of non-persistent. In the non-persistent, you sense if the channel is busy, then you wait for some time, and then you sense. If you find that the channel is busy, then you wait for some time, and then sense. So let's analyze this compared to this. On one hand, the channel has been idle here, right? And you didn't feel it until here. صح? Which means that you have missed this time to access the channel. So during this time, the channel was idle and you didn't pay attention to that. So you missed this time, you wasted this time, which affects a little bit the efficiency or the utilization of the channel, right? So on one hand, waiting for this time was a little bit bad, but you know what? It's good in a way. Why? Because it reduces collision. So the non-persistent will be bad if the channel load is low. If the channel load is low, then the probability of collision is very low, right? In which case, you better utilize the channel is idle, because if the channel is idle, try to send, because if the system is loaded, is underloaded, then whenever you try to send, the possibility of collision is low anyway. In which case, the non-persistent strategy will not be efficient. But if the system is highly loaded, then it's better to use the non-persistent. And guess what? The efficiency of the non-persistent is more than the one persistent. So in the one persistent strategy, the efficiency of the system is not more than 70-75%, which is, again, it's more than pure Aloha and slotted Aloha for sure. So it's almost double, which is good. But for the non-persistent, it can get up to 90% if the system is highly loaded. Which means that you give a chance for someone else to gain the channel before you. And if that happens, then at this point in time, you will sense again and you will find that the channel is busy, and then you abstain. which means that because this wait time, this wait time is not synchronized between the nodes. لاحظ. This wait time is different. This wait time is different from one node to another. So you don't have to have synchronization when exactly to sense amongst all the channels. So there is a possibility that another node will try to send at this point. And then the frame will start. So once you sense here, you will find that there is a transmission happening and you will stop. Okay? So this wait time, in fact, it's good and bad. It's good from the sense that you try to avoid collision if it happens, especially if the system is highly loaded. And it's slightly bad if the system is underloaded because the possibility of collision is low. And this wait time, you don't have to wait because, if you try to send, the collision will not happen because the system is underloaded. But you prefer to wait a little bit and waste a little bit of time. Okay? So this is the non-persistent strategy. So we sense at slotted instances of time. So this, عشان كده بقول, this is actually, in a way, takes a mechanism which is close to pure Aloha. You keep sensing continuously, and once the channel is idle, you send right away. And this uses the slotted mechanism for sensing. You don't sense all the time. No, you sense at instances of time. So, in general, the slotted system always has better efficiency, especially in high load. Why? Because in high load, if you don't have any slots in the system becomes messy. You can send or you can sense at any point in time, and once you find that the channel is busy, you send right away. There's no preset times for sensing or for transmission, in which case you end up with lots of collisions happening. Okay? Okay. So for that case, what we said here is that there is a possibility that if the system is underloaded, the non-persistent will not be that good, because you waste a little bit of time, and the collision is less probable. So in that case, you wait for a time that you don't have to wait. And the one persistence is actually turns out to be bad if the system is loaded, because if the system is loaded, the collision will be high, and then you try to send right away, which means that you increase the collision. The third strategy adopts a mix of both. Okay? It adapts a mix of both, which means that we will not try to miss any gaps. We will not try to miss any gaps. Okay? So we want to detect when the channel becomes idle. But when the channel becomes idle here, we will not send right away. Okay? So we will all detect that the channel is idle here. So multiple nodes will detect that the channel is idle here. Okay? But we will not send right away. At this point in time, what we will do is that we will flip a coin. Okay? or generate like a random number. If this random number is less than P, only then we will send. If this random number is more than P, we will not send. Okay? And if I don't send, I will wait for one full time slot. Okay? And here, I will do the same. I will check channel is idle or not. If the channel is busy, then I will go back to the continuous sensing until the channel becomes idle. If the channel is idle, then I will flip a coin. I will generate a random number. If it's less than P, send. If it's more than P, you don't send. Remember that in all cases, we do not eliminate collision. We will not be able to eliminate collision. So there is still a possibility that the collision will happen. So what is the purpose of the P persistence here? The P persistence strategy turns out to have efficiency which is more than both. The P persistence here tries to avoid missing any gaps which happened in the non-persistence case. So we will detect that the channel is idle once it becomes idle. And at the same time, we will use some kind of a random back-off procedure. Remember the exponential random back-off procedure that we have discussed in Aloha? The P persistence uses a similar mechanism. So all the stations will generate the random number. Okay? Hopefully, if two stations are trying to access or contend on the channel, if they generate a random number, hopefully this will prevent one of them from sending. So the other one will send, so collision will not happen in that case. So by flipping the coin. It's like if there are two stations, we will flip the coin, only tail can send, something like that. Okay? And P here, remember that P here doesn't have to be 50%. P is the persistence probability. So we can, it's like a tuning parameter. We can increase it or decrease it. If P is 1, this means what? This means we'll go back to one persistence. Which means that once the channel is idle, we send with a probability 1. That's what this means. Okay? But here, we'll generate a random number. If it's less than P, then send. If it's more than P, then don't send. So we can sort of fine-tune the system to make it very persistent or less persistent. Okay? And if I don't send, then I have to wait for one full-time slot. One full-time slot here, it's enough for one station to send one frame. And then after this time slot, I will check if the channel is still idle, then again I will use the random back-off procedure. If the outcome is the fact that I should not send, then I wait for one time slot and so on. Okay? So these are 3 persistent strategies that can be used for the carrier sense multiple axis, depending on whatever, like some standards, they use one strategy over the other. So for example, the early versions of Ethernet, they use actually the non-persistence. The non-persistence strategy, it's used as part of the Ethernet. Okay? Later on, for the case of later versions, gigabit Ethernet and stuff, they started to use the P persistent. Okay? So it's like this one tries to resolve the problems in the two by utilizing the channel when the system is underloaded, and at the same time avoiding collision if the system is highly loaded. Okay? Any questions? So this is the flow chart that corresponds to the three persistent strategies. For one persistent, it's very easy. Channel is busy, channel is busy, channel is busy until the channel becomes idle, then send. There's no intelligence here. For the case of non-persistent, if the channel is busy, then you wait for some time, random time. We said that this time is different from one station to another. And then you sense again. Okay? In that case, during this time, the channel might become idle and you don't feel it. Okay? Then you miss some window of time where the channel is idle and you did not utilize it. So, the P persistence, what it does is that this loop, as we can see, this loop is similar to this. صح? So this loop is similar to this. And then if the channel is idle, now we're talking. So we will draw a random number. We will try to generate a random number. If this random number is less than P, this means you can send. So just send. Okay? If this random number is more than P, this means that you will have to wait for full time slot. Not a random number here. You will have to wait for a full time slot, which is enough for one station to send one full frame. Okay? And then you will again sense whether the channel is idle or busy. If the channel is idle, then you go again and you generate random number again until the random number is less than P, in which case you can send. Okay? So that's the P persistent case. Type. So that slide here shows the case of collision detection. So we all know that Ethernet uses carrier sense multiple access with collision detection. Okay? So when does the collision happen? When and where? Okay? And when can any station feel it? So the answer for the first question and the second question are different. Okay? So when does the collision happen in time and space? Might be slightly different from when any station will feel that this collision has actually happened. Okay? So for example, if A tries to send, this will not reach to C until this point. And similar to the previous example, C here will sense channel is idle, then it will send. So C will detect the collision at this point. The actual collision happens where? The first time at this point. So this is when the collision first occurred. Okay? So the collision actually happens here. C will detect the collision at this point. And A will detect the collision at time T4. So at time T3, C will detect the collision, and at time T4, A will detect that there is a collision. Okay? So that example is easy. So as a motivational question, A will start sending here. Okay? A will start sending at time t1, right? It will, remember, at time t1, I will start sending my frame. صح? When do I finish sending the frame? This graph doesn't show. I will start here, but when do I finish sending the frame? I did not show you that here. Okay? طيب. When did I detect that the collision happened? At time t4. Okay? So, what happens if A finishes transmission at time before t4? What is the behavior? So I started sending the frame here. Remember, while sending the frame, I listen to the collision, right? What happens after I finish the frame? I finish sending the frame. What happens? What do I do? I finish sending the frame. What do I do? Nothing. Why do I need to do anything? I started sending the frame, I finished sending the frame. During the transmission of the frame, I did not detect any collision, right? What do I need to do? Nothing. خلاص. The frame has been sent. For me, the frame has been sent. يبقى if A finishes transmitting the frame in any point before T4, for A, this frame has been sent successfully. Remember that Sysma CD does not use acknowledgement. It uses only negative acknowledgement. Only negative acknowledgement if the frame arrives on the other side and the other side cannot decode it. Only then the other side will send negative acknowledgement and I will hear it. I will detect that this frame has not been sent correctly, so I will send it again. But in normal cases, I will, because I detect collision, I don't need acknowledgement. So the two possible scenarios for losing the frame is either the frame arrives and it cannot be decoded. Either the frame arrives and it cannot be decoded, or the frame collides. Because I detect collision, I don't need acknowledgement in that case. So in normal cases, I don't need acknowledgement. So if A finishes the transmission in any time before T4, it will consider that this frame has been sent successfully. Why do we ask this question? So this scenario tries to motivate the fact that we should not use very short frames. We cannot use very short frames. بمعنى إني when I start sending the frame at this point T1, okay, and we said that A will detect the collision at time T4, right? So the minimum frame length has to span from T1 to T4. Because if it's less than T4 minus T1, this means what? A will figure out that I sent the frame, during the transmission collision did not happen, therefore this frame has been sent. But is that true? No, this is not true, because the collision actually happened here, but I didn't feel it. But you didn't feel it because you're using too short frame. You are using frame length which is too short. So in that case, I should increase the frame length. When I say that the frame length is T4 minus T1, we don't measure the frame length in time, right? We measure it in bits. But what does that mean? This means that the time is the length divided by the maximum data rate, right? But this is constant. The maximum data rate is one maximum data rate for the channel, right? So if we multiply this time by the maximum data rate, we can get the length in bits. صح؟ يبقى the transmission time equals the data length divided by the maximum data rate, right? So the length of the frame is actually the transmission time multiplied by the maximum data rate. So if I have a time span like this, I can know the length of the frame that can span this time by simply multiplying by the maximum data rate of the channel. So I can multiply this time by the maximum data rate. I get the length of this frame in bits. Okay. طيب. We still did not answer the question now. What is the minimum frame length in that case? Well, the minimum frame length happens when the signal travels all the way, then someone detects that the collision has happened, صح? And then it should try to send something back which causes the collision to happen. Okay? And then I measure the span of time multiplied by the maximum data rate. Then I get the shortest length of one frame, which I should use a frame length which is more than that. Okay. What is the worst case scenario? The worst case scenario is when A is in the beginning of the cable, C is in the end of the cable, okay, and it happens like this. So add A, so A sends the frame, so it reaches to C. Slightly before it reaches C, يعني half a nanosecond before it reaches C, C checks that the channel is idle, so it sends the frame. Remember, this time is what? Is TP. This is the propagation time. صح? Slightly before the end of this propagation time, C checks that the channel is idle, then it sends. Then it goes all the way to A. So from this point, it takes another T propagation. And A will only detect the collision at this point here. Okay? يعني again خلينا عشان تبقى واضحة أوي. The worst case is that A is in the beginning of the cable and C is at the end of the cable. يعني if I give you the cable length, you can get, this is the worst case. So A tries to send at this point, so it sends which takes a propagation time. Okay? But slightly before that time, C detects the channel, it finds that the channel is idle. So it sends the frame. The collision will happen very close to C. صح? What is this time? That's T propagation. صح? So this is one T propagation and this is another T propagation. Okay? So the collision happens يعني almost at C, but A did not feel it until 2 propagation times. Okay? So I sent at time 0. After 2 propagation times, only then I can detect it. So what is the length of the shortest frame? In worst case, is A? 2A? 2 propagation time. Okay? This is the length of the shortest frame in time. In bits, it's A. I multiply by A, by the data rate. That A, that gives me the length in bits. So, okay, well, so until here is clear. So the minimum frame length is actually 2 propagation time.